All right, so we said in this video we're going to start with getting into causal attention because in the previous one we introduced trainable weights, but there was one problem with what we did. We did say we are going to do masking, but what do we mean when you say we are going to do masking? So let's see in this video what we mean. So causal attention. This is now the number 3, right? The third version of attention that we said we are going to discuss. We first started off with a very simple one that didn't have any trainable weights. Then the second one we went into had trainable weights. But then now we are moving to the third one that has something called masking. So the problem with what we did is many LLMs they um they predict based on tokens that have appeared prior tokens and current token. And we know that. That's how they work. And current token. So when they're doing that next word, that's what they take into account. Or when they're predicting the next token. But if you remember what we're doing, we're showing all the tokens to the LLM. And that's not exactly what happens. So causal attention, it allows us to mask certain tokens. It's also known as masked attention. So this one is also known as masked attention. It's a specialized form of self-attention which restricts the model, um, restricts restricts the model to only consider previous and current inputs in a sequence when processing any given token. So when we're computing attention scores, etc., we do not consider tokens that are in the future. So let's see how that happens. So we're going to modify our original token. So imagine this was what we had, like journey, your journey starts with one step, starts with one step, and this will be columns like this, right? So imagine there are columns like this, and here we have your journey, and these are the rows. And here what we had numbers that we had numbers here, numbers there, numbers there, in a 6 by 6 matrix like that. That's what we had, right? Then there's a step right at the end. That's what we had. Numbers everywhere. But that didn't make sense because if we are dealing with journey, why should journey know about these numbers here that are coming after journey? These numbers that are coming after journey, they should be hidden because the model should not even see these. They are in the future. Journey should only see your and journey. Those are the only two that journey should see. So let me get something to actually show you exactly what I mean here. So uh okay. This image is going to explain exactly what I mean. So let's get back here and let's just quickly paste this image. Where did it paste in? I don't see it. Okay, there. So this image is going to explain what we mean. I'm just pushing it up so that we keep a bit of space at the bottom. Yes. Perfect. So this image there, as you can see, this is our original one where we're doing even the simple or the standard self attention. Every token had access to every other token, no matter where it was. But then now we are masking to say if we are at position yo, it should only know about yo, which is the current position, and anything prior, not anything in the future. So we are masking by the diagonal. By the diagonal. Journey, Journey now knows about yo. You see yo here, and its current, which is journey. Fine. Starts knows about your journey starts, but does not even know what the future is going to be with one step because this is what we want to predict in the future. And then same with width. It only knows all the way up to width and not anything and not anything after that. One, same, step, same. So we want to do what that diagonal masking. So we mask by the diagonal. So let's see how we can do masking by the diagonal. If we can mask the top right corner, we would have done well. And we are going to do this in such a way that each row still adds up to 1, adds up to 1 at the end. So as you can see here, this row adds up to 1 because it's just 1. 0.55 plus 0.44. Of course, there's going to be rounding off errors because here we just truncated to these two decimal places, but this is like 0.99, which is 0.1. Same as if we add these, they're all adding up to 1. Like we had previously, here they were adding up to 1. They are now slightly different numbers, but they were adding up to 1 because we masked out some other tokens and all of that. So let's see how we do this. So we are going to we can do this in two ways. The first way is to mask with zeros. We can mask with zeros. So what we can do is we have our attention scores. We have our attention scores, right? And these attention scores, they are anomalized. As we know, they are anomalized. And what we can do is we apply soft marks, right? Because when we apply soft marks, we now get our attention weights. We get our attention weights. And when we get our attention weights, these are now normalized. And we mask with zeros above diagonal, right? Above diagonal. And after we do that, we now have our masked attention weights. Okay, we get back to scores. Let's get back to scores. We get back to scores because they are not normalized anymore. They become unnormalized, right? They become unnormalized because once we because these are our attention weights, and if we just mask these to be zeros, then the row doesn't add up to 1 anymore, so they become anomalized, right? Become anomalized, and then we normalize values, and then we get back to masked attention weights. Now we've masked attention weights, not scores anymore. Then these are normalized. So we can do this in these steps. Soft marks first step, second mask those weights that have been created by these weights that have been created. We mask them with the zeros, and then third step, we normalize we normalize the values. We normalize the values. So we can do that in 3 steps like that. So let's see how we are going to do that. How we are going to do that in code. So let me quickly switch to Google Chrome. Great. So in Google Chrome, yeah, where I'm using my Google Colab, these we are just using that self-attention V2 that we had to create the first phase, which is the attention weights, normalized and all of that, but not yet masked. So that's what we have here. As you can see, we have our matrix 6 by 6 unmasked like we had previously. So let's continue from there. So simplest way is for us to replace whatever is on the above the diagonal with zeros. We can do that. We can create this mask matrix that is the same dimension as our attention weights matrix. So it'll be 6 by 6. We just used this to get the shape 6 by 6. Nice. And then we create this mask. We're using this function called trill. It's a function in PyTorch. And so now what we have is the bottom triangle here has ones, and the top triangle will now have everything above the diagonal will have a 0. Brilliant. So as you can see, if we multiply our weights matrix by this one, which is ones and zeros, we get a result that is zeros at above the diagonal. So that's what we are just doing here. Simply multiplying like that. And as you can see, we've maintained the bottom triangle and the top has been turned into zeros. Perfect, straightforward, I would imagine. Then now, if we apply the soft marks here, it will disrupt our probability distribution. So what we can do now, because we have a third step. We have that third step because now we have these masked attention weights. We have the masked attention. No, they are scores now. They are masked attention scores because we came back. These were the attention weights. When we applied the mask, they went back to being attention scores because they're not adding up to, they're not normalized anymore. They're not adding up to one. So now, if we apply soft marks to this, we will disrupt the probability distribution. So what we can do is we can just do a different version of normalization. We do a sum normalization. So pretty much per every row, sum them up, and then divide each element by that sum. We saw this type of normalization back when we were starting with a simple attention um, variation. We tested this one where we summed and then we replaced it with soft marks. But here we can use it. So we're just summing up per row, like we're doing here, sum per row. And then, so when I'm saying sum per row, it's saying in each row, sum up the columns. That's why we are doing dimension minus one, because it's going to say, okay, I'm summing up throughout the columns. So each column 1, 2, 3, 4, 5, I sum them up. It's summing across the columns. So because this is column number one, column number two, column number three, it's going to sum across the columns like this and then get a result that it will store, let's say on this side. And that's pretty much summing up the row itself. So each row will have its sum, and then each element in that row will be divided by that sum. So here we're going to have, because these are zeros, we're going to have 0.1921 as the sum of this row, first row, and then we divide each element by that sum. So 0.1921 divided by 0.1921 is equal to 1, and everything else is 0. So that's why we have a 1 here. And we're going to do for all the other rows. And when we add them back up, we know that we know that they are all going to add up equal to 1. So now we have normalized them again. So these are now the masked attention weights after our third step. These are now masked attention weights that have been normalized. We can do this, but there's a trick in mathematics that we can use. The trick is in infinity, when you use the softmax function in infinity, our softmax function, the formula itself, it uses, let me see if this will show the formula. Yeah, I believe it is showing the formula for softmax. So this is the softmax function. If that's the softmax function, right? If we put negative infinity here, and then we sum up very small values, they're going to be very, very tiny values. So we are going to have negative infinity. This will tend towards zero. It'll go towards zero. And this will be a sum of very, very small values. So the whole thing, the softmax, will tend towards zero if we apply softmax there. So we are going to use that trick. So let's see how we're going to use it. So instead of doing these three steps of masking first with the zeros and all of that, what we can do is, instead of zeroing out the attention weights above the diagonal and renormalizing them and normalizing and renormalizing and all of that we did in three steps here, we can mask the unnormalized attention scores above the diagonal with negative infinity. So what we have is we have attention scores. So here we calculated our attention scores, right? Here. So instead of calculating the attention weights and then normalizing those attention weights, because that's what we did, calculated from attention scores, we did softmax to get the attention weights. We masked these, then we went back to some other attention weights, and then we normalized the attention weights again. Instead of doing that, let's skip this step of calculating attention weights. Let's get our attention scores. When we get our attention scores, what we are going to do is, for those attention scores, we are going to fill anything that is above the diagonal of those attention scores, the raw attention scores that we just got from query and key. We mask them with an infinity on top them. So anything above the diagonal of our raw attention scores that have not been normalized yet, we just fill them with an infinity. Because we know that if we apply soft marks to this row, soft marks is going to make sure that each row adds up to 1, but also the minus infinity goes to 0, just becomes 0. So we are killing multiple steps in one step. That's all we're doing there. So that's what we are now doing straight from attention scores. So here we've calculated query keys, attention scores. Then from attention scores, we're filling them with minus infinity. When we fill them with minus infinity, we then apply our soft marks straight. Apply our soft marks with our square root, with our square root here, with the embedded dimension. That's it. And soft marks make sure that each row adds up to 1. And also minus infinity goes all the way to 0 because of this function, its function itself. E to the power of minus infinity is equal to 0. And then the summation here will be very, very tiny number. So it's 0 divided by very, 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 very tiny number. It's pretty much equal to, like, we can say it's 0. It's 0. So everything becomes 0 if it is a minus infinity. So now we have masked the top part and we have created our attention weights without having to attention scores to our full block attention weights that we mask with zeros. Then we do this without doing that. We're just doing it in one step like this. So now this is now our masked attention weights, and that's it. That's what we wanted to show here. So there's one thing that we are going to tweak when it comes to this causal inference, which is extremely important even when we are doing normal training of normal neural networks. Even if you're doing convolutional neural networks for images and all of that, it's extremely important. So let's see that in the next video.